here are how we find the volume of a solid of revolution. You'll notice they're basically the same, except for if you're rotating around the horizontal axis, you have an x here and a dx. And if you're rotating around a vertical axis, you have a y here and a dy. So, if you pick apart the pieces of that equation there, you've got pi, you've got this equation, and it's squared. What does that remind you of a lot? Area of a circle, right? So you've got pi r squared would give you the area of a circle. So when we do this first problem, I'm going to show you how that kind of is the same. Oh, I opened the wrong thing. Let me open the ones that are not already filled in. Okay, so here's our first equation. I'd get the key points of it. Main thing you need are your equation and equation, x-axis, and we're revolving about the x-axis. And it also tells us from 0 to pi. So the question asks us to find the volume of the solid formed by revolving the region bounded by the graph of f of x equals sine x in the x-axis from 0 to pi about the x-axis. So it's a good idea for these to try to get a graph before you actually do the problem. Sometimes they may be too complicated and you may have to kind of figure out how to do it otherwise, but something like the square root of sine x, I don't know how to graph very well, but I am probably going to be able to figure it out. So this is at pi, and let's just make us a little table here. I'm not going to know lots of the values for this, but if I plug in 0, what is the square root of sine of 0? 0, right? So I'm going to have this point here. And then I could plug in, let's see, this would be pi over 2. Think unit circle values for this are probably going to be the easiest. So if I plug in pi over 2, what is sine of pi over 2? And the square root of that is 1. So I have, mark 1 on here. So I have this point here. And then square root of pi, or square root of sine of pi would be 0 again. So we know sine normally just looks like that curve and then it continues. So these are the same points as sine. Just so we can see a perfect one, I'm going to graph it in Desmos to y equals. Let's see, I'm going to graph sine x, and I'm going to graph y equals square root of sine x, just so we can see the difference. You'll see that, we really only care about from 0 to pi. I'm going to make this pi over 2. And so you can see here, it's really about the same shape, except for it's like a little bit higher on the edges that blue graph is, right? So for all of our purposes, we can just draw it in like a sine graph, really. So we have this shape right here. So what we're going to do here, and I should have found another animation, but what we're going to do here is we're going to take the this line and we're going to rotate it about that x-axis. So it's going to make it some sort of, kind of like a football shape a little bit, probably maybe, well, depending on your scale. My scale's probably off a little bit. Might be, mine looks like it'll be a fat football, but, so we're going to have that shape when we're done. So our equation pretty much is the area of the circle, and then we integrate it from 0 to pi, and that'll give us sort of multiplied by that length. And the radius, if you think, if we're rotating around the x-axis, it's like we're taking this little slice right here, and we're rotating that around there, and it would make, this is called the disk method, because it would make a circle if we did that. And then you're taking, you know, the piece next to it, and you're rotating it around and making a circle. And the next one, rotating it around and making a circle. So pi r squared gives you the area of that circle, and then integrating it from 0 to pi adds all of those circles together. All right? So since we're rotating around a horizontal axis, our everything's going to be in terms of x, which is good because our equation is already in terms of x. So we will, to find our volume, we'll do pi times the integral. And technically, you could put the pi on the inside if you want, but it's just a coefficient, so it's a little easier to integrate if you leave it on the outside. And we would integrate from 0 to pi. Our intervals come from the x-axis, since we're integrating with respect to x. And we would have the radius, which is the square root of sine x squared dx. So pi r squared, and then integrate from 0 to pi. So this one actually turns out not to be so bad. The square root actually makes it easier to do in this case, because whenever you have that square root squared, we're just getting the integral of 0 to pi of sine x dx. And whenever we integrate sine, what do we get? Negative cosine. So volume equals negative. Well, yeah, I'm going to just go ahead and put that negative out there with the pi. Negative pi cosine of x. And then from 0 to pi. And then so that'll be cosine of pi minus cosine of 0. What is cosine of pi? Well, I put the negative out here with the pi. You could keep it with the negative, with the cosine if you want. Cosine of pi is negative 1, and what is cosine of 0? 1. So you're going to get negative pi times negative 2, which is going to give you 2 pi. And this particular problem did not have units, but it would be units cubed because it is volume. So if you use this to create your football, and then you needed to know its volume so you could tell how to properly inflate said football. You could. You could. We might should try some reverse engineering stuff like that. Like bring something in that could be created with that and see if we could make the right equations for it. We might do that. Yeah, like a water bottle would be a good one. You know, something like a flower vase or something.
You could do this stuff in like manufacturing, right?
You would. I would say it depends on how.
Like if they're making like 3D printed stuff.
Yeah, you would think so.
They're making like, what do they make with 3D printing nowadays?
Well, you know, like somebody, whenever they made that water bottle, had to make sure it would hold 1 liter of water. And you don't want a lot of, like, you don't want it only half filled. So I feel like that water bottle probably had something to do with that. Maybe. It would be nice to know. Or maybe they just play with it till they get something that holds a liter, but
Maybe they just have like a mold.
but I feel like that would be good to know. But I think this stuff is so cool. It just looks so cool. I wish that there was a program that would like take everything that we do and rotate it around the axis for us so that we could see it. But I have yet to find. All right, so sometimes, and I could tell on the quiz it was also kind of confusing to you guys. Sometimes I have a little bit of hard time with the y equals and x equals lines because no matter, I mean, even though you've done them for a very long time, remembering which one's vertical and horizontal can still be a little bit tricky. Y equals 0, what kind of line is it? Horizontal, it is the x-axis. And x equals 2, that's vertical line at x equals 2, right? So that sort of helps you picture what you need to know. If you plug 2 into this equation, what are you going to get?
8, 9.
9. So that sort of lets you know, like, if you're trying to graph this, how far up you need to go to graph it. So we really only need first quadrant here. And we really only need to go from 0 to 2 on our x-axis, but we need to go to 9 on the y-axis. So, like if we're graphing x to the third, actually we do need a little bit of second quadrant, don't we? Yeah, we do. Because we're using the x-axis as one of our boundaries. We're using this y-axis, or not y-axis, this vertical line is one of our boundaries. And then x to the third plus 1, which would be, it would have a y-intercept at 1, and then if we plugged in 1, we'd get 2. If we plugged in 2, we'd get 9. But if we plug in -1, that's where we get 0, so it doesn't hit the x-axis until there. So we do need a little bit of that second. Okay, so we're taking this, I'm going to highlight that area there that we're looking at because not got the right area, you'll have a hard time picturing what you're rotating. And so this is going to give us a little bit of that sombrero sort of shape whenever we rotate it, because we're going to have like these vertical pieces right here, and they're going to rotate around this way to make a circle. And so that radius here is just that green line, because that green line gives us the distance from the x-axis up to that point, right? So we are going to have, in this case, pi r squared, so we're going to have pi times the integral. What do I integrate from? What are our limits of integration here? -1 to 2. And then we'll have x cubed plus 1 squared dx. Because it's like a circle. So what the pi could be on the inside if we wanted. So if we do like pi times the equation squared, that would give us the like area of one of the little circles, right? So like if you think of this just being a series of a bunch of little circles all next to each other, discs, that's why they call it a disc.
guy pulls up a little thing.
Uh-huh.
And it has like the separated circle.
Yes, that's a
And
good.
it's like a,
Yeah, so like each little, on his little honeycomb dipper, yeah. On his little honeycomb dipper, each one of those little discs makes his little dipper there. So, like, we're taking, like, pi r squared would give us the area of one of those. And if they all were like wafer thin, right, like, didn't really even have any width, and we added them all together, that'd give us the area perfectly. So, integrating adds all those tiny little discs together.
So it's like you have to do your equation that gives you the line, then you have to integrate it so you know what's actually going to do, and then you multiply that by 5%.
Yes.
Okay.
So once you get this set up, it's really just a matter of integrating. So I would probably go ahead and square that out. Also, don't lose that pi because it's so easy to lose the pi there. So we would have x to the 6th plus 2x to the 3rd plus 1. If we did square, double square for that. And then we would have to integrate. Oh, let's see. I don't need that integral symbol anymore because I'm integrating. So I would have 1/7 x to the 7th plus 1/2 x to the 4th plus x. And that has to be evaluated from -1 to 2. And on one like this, if you get one like this on your homework, let's just grab the calculator and see it from here on out, because I am sure that we all could, if we wanted to, maybe get the right answer if we had to do this, but that is not the main thing I want to see. The 1/7 times 2 to the 7th plus 0.5 times 2 to the 4th plus 2. So that gives us, see, I'm just going to pi, that gives us 28.2857. Probably should have left it not a decimal so it would give me a pi, but that's okay. It'll work out. And then 1/7 times -1 to the 7th plus 0.5 times -1 to the 4th minus 1. That's going to give us -0.642857. I bet that I should have done that with a pi probably. But this plus this. Oh wait, I should put minus. So we'll just go ahead and multiply that by pi since I've already done decimals here. The book probably won't use decimals. The book will probably give you like 32 pi over 7 or something, but since I typed it in already, there's no going back now. So 90.8818 units. So that would be the volume of your sombrero shape there. And we're going to stop here because we don't really have time to finish another problem. I'm going to give you just a couple to you for homework. And we are going to do 1 through 4 on page, what page is this? 425. So page 425. I want you to do number 1 through 4. And the good thing about this is that the book gives you the graphs, so you don't have to actually craft them by hand for that. So 1 through 4, I think all of those are ones that we can do pretty easily.